Hello everyone. In this example, we're going to cover the concept of the electric potential of non-uniform electric field, the electric potential that generate from the single charge particles. Here in this example, we have identical two charges, one positive, one negative, with the same value, which is located at the distance of 4 meters from each other. And we're going to calculate the electric field and electric potential, first of all, at point A, which is located at 1 meter away from the positive charge. After that, we're going to calculate the electric field and electric potential at point B, which is a midway between two charges. So let us start with the point A. So at point A, we're going to calculate the total electric field. Electric field is a vector. So we have vector summations of the electric field that generated by charged particles 1 and charged particles 2 at point A. So let's consider this charge as a Q1 and this charge as a Q2. Q1 is positive, so the electric field is going to be going away from the positive charge, and Q2 is negative, and the electric field is going to be toward the negative charge, E2. So both electric fields are at the same direction, so the vector summation can be simplified with the simple summation of these two electric fields at point A. So let's take a look at the electric field that's generated by charged particle Q1 at this point. So Coulomb constant, the charged particle Q1 at distance of the charge from distance of the charge 1 from point A, and the electric field at point 2, Coulomb constant, charge Q2, and the distance of this charge from point A. So I'm going to put all of these information here. Charge Q1 and Q2 are equal in the magnitude, so we can write it and factorize this term from both electric field. So from the first term, we have 1 over R1 in power of 2. From the second term, we have this one. So if I put the Coulomb constant, which is 8.9910 power of 9 Newton meter in power of 2, Coulomb in power of 2, multiply with the amount of charge, which is 1 microcoulomb in the absolute value, microcoulomb to coulomb, and for the first term, we have the distance of the charge 1 from point A, which is 1 meter, that's 1 meter in power of 2 plus 1, and the distance of charge Q2 from point A, which is 4 meter minus 1 meter, which is 3 meter in power of 2. So we will have the electric field as point A equal 1.010 power of 4 Newton per coulomb. The first term is going to be 1 over 1, and the second term is going to be 1 over 9. So now we're going to calculate the potential at this point. Potential at point A. So the potential is the scalar quantity. So the potential doesn't have any direction. So we need just consider the potential that single charge particle Q1 generated at point A plus the potential of charge 2 at point A. So the potential following this equation, charge 1, the distance of charge 1 to point A, plus the Coulomb constant, the charge particle Q2, distance of the charge particle to specific point, point A, that you can see here. So again, one charge particle is positive and the other one is negative. Whenever we're going to calculate the potential, we have to consider the sign of charge particles. So we have the Coulomb constant, Q1, distance of the Q1 from a specific point, and Q2, the distance of this charge from the point A. So Coulomb constant, 10 power of 9 Newton meter in power of 2 Coulomb squared multiplied with this parenthesis, which is charge 1 microcoulomb converted to the coulomb, the distance 1 meter minus, or we can put plus, and the charge 2, which is minus 1, 10 power of minus 6 coulomb at the distance of 3 meter. So we can calculate the potential at this point, which is 6, 10 power of 3